Okay, on this computer. Okay, thank you guys for coming here. It's my pleasure to introduce Kevin Ford, and he will talk about the anatomy of random integers, permutations, and polynomials. Thank you very much, Kevin.
Yeah, well, thank you for inviting me to speak in the seminar. Now, I know from the abstract, if you read the abstract, it sounds somewhat similar to the talk that Dimitris Koukoulopoulos several weeks ago. But in fact, there's only a small overlap between my talk and his. My focus will be slightly different. Right, so I want to talk mainly about the connection between random integers, random permutations, and random polynomials over a finite field with respect to factorization. Okay, each of these objects has a unique factorization, right? Integers factor uniquely as a product of primes, permutations factor into cycles, and polynomials, of course, factor into irreducible polynomials. So 3 meta questions that we can ask. If you take a random integer, let's say below x, how are the prime factors distributed? You can ask a similar question about a random permutation with respect to the cycle lengths. Okay, so the cycle lengths tell you a lot about the permutation, especially the group theoretic properties. And the same for a polynomial over a finite field. What can we say about the distribution of the sizes of the irreducible factors? Okay, so these are 3 sort of basic meta questions. We can also look at divisors. Now for the integer setting, divisors are well understood. Right? A divisor is just a product of some of the prime factors that divide n. Divisor of a permutation, I'm going to define it to be the product of some of the cycles in the random permutation. So the cycles play the role of primes, and then the divisors are a product of some subset of these. And for polynomials, the notion is pretty straightforward. You multiply some of the irreducible factors and you get a divisor. So it's another polynomial that may or may not be irreducible. All right, and throughout the talk, I'm also going to be following this color scheme. So blue boxes refer to integers, green for permutations, and red for polynomials. All right, so those are some meta questions. What are the kinds of, so here's some examples before I get into the theory. So here we have an integer in the blue box. So look in the blue box, have an integer. There's the list of its prime factors, and there's a list of its positive divisors. All right, so these are then products of various subsets of the prime factors. You can also look at on a logarithmic scale. The logarithm of the divisors come from looking at the sums, the subset sums of these numbers log 2, log 3, and log 7. Okay, that will be important in the next 2 examples. So if we look at, here's a permutation in the symmetric group on 9 elements. It has a 2-cycle, a 3-cycle, and a 4-cycle. So the cycle lengths are 2, 3, and 4, and the divisors, the possible divisors, have lengths 0, 2, 3, 4, 5, 6, 7, and 9. So for example, how do I achieve the divisor of length 5? Well, I take the cycle of length 3 and the cycle of length 2, and I multiply them together, and that gives me a divisor of length 5. Okay, and these are, so this set of numbers here is in fact exactly the set of subset sums of the cycle lengths, the set of cycle lengths. A very direct analog is this example in the finite field F2. So this 9-degree polynomial factors as a factor of degree 2, degree 3, and degree 4. So those are the factor degrees, and the degrees of the divisors. Well, it's the same list because it's the same problem. We're taking 2, 3, 4 and computing all the subset sums. All right. So those are some basic examples that illustrate the concepts, and you can see the connection here. So how you achieve or how you obtain divisor lengths or sizes through some subset sum operation. All right, so what do we know about random integers and the prime factors? Well, this is very classical. It began, well, even before Erdős's work. There was the earlier work of Landau and Hardy and Ramanujan, but it really, Erdős was the first to look at it from a more general point of view. So if I take a random integer up to x, and I ask the question, how many prime factors does that integer have in an interval AB? So that turns out that that statistic, so this is now a statistic of the random integer n, behaves very much like a Poisson random variable with parameter log b minus log a. And moreover, if I have independent if I have disjoint intervals, then the statistics for the disjoint intervals are approximately dependent. Right now, nothing is exact here, so I'm hiding some error terms under the squiggle sign. So for example, if I have an interval of the size of the type e to the k up to e to the k plus 1, then the number of prime factors in that interval behaves very much like a Poisson random variable with parameter 1 over k. Now, where the log comes from is pretty easy to understand. Naively, if you have a prime and you take a random integer, the probability that that integer is divisible by that prime p is very close to 1 over p. Okay, that's the naive probability, is it would be exactly 1 over p, but depending on what x is, it could be slightly off. And then if we compute just using simple estimates, what is the expected number of primes of a random integer in this interval? Well, it'll be the sum over these primes of 1 over p, which by Mertens gives you these this difference of logs. Okay, so this log comes up very naturally in the study of prime factors. Okay, and Kubilius, using the sieve, found a very general form of this, which implies in particular that this independence works for many intervals at the same time, provided that you stay away from x. Okay, so you don't want, if b is say x to the little o1, then this will be true. Otherwise, there's a slightly different distribution. But for the moment, we'll just take this as a basic property of prime factors. What about cycles of random permutations? Well, this also has this Poisson statistic. If we look at C sub k, which is the number of cycles in a random permutation that have size k, this also behaves like a Poisson random variable with parameter 1 over k. And moreover, as was proved by Aratia and Tavare in 1992, this vector of statistics is these are approximately independent as long as T is small compared with M, which is the size of the symmetric group. So for small cycle lengths, we have this vector then behaves similarly to a vector of independent Poisson variables with this with these parameters 1 over k. And the idea here is a little simpler, using a very old and relatively easy formula of Cauchy. If you want to take the random permutation of SM and ask what is the probability that it has a given cycle type, that is R1, 1 cycles, R2, 2 cycles, and so on, there's an exact formula for it. Okay, which there's no analog of this in prime number theory because the primes are very irregular, but with cycle lengths of permutations, we have a very exact formula. And each factor here looks exactly like a Poisson random variable with parameter 1 over j. Okay. The only caveat is that you have this conditioning here. Of course, the sum of the cycle lengths has to equal m, and that's the main complication that one encounters when one is trying to prove anything about these. All right, so that's where Poisson random variables come from in permutations. What about polynomials? Well, here we can take 2 points of view about what we consider a random polynomial. So the first was taken by Chebatarov nearly a century ago. So you fix an irreducible polynomial, irreducible over the rationals, say degree m, and we look at its reduction modulo primes for all the primes and gather statistics on the factorization modulo p. So if we let g sub j be the number of degree j irreducible factors, and then the vector g1, g2 up through gm will tell us what I'll call the factorization type of the polynomial. So if we count how many primes up to x have a given factorization type, divide by the total number of primes up to x, as x goes to infinity, this approaches this same product. Okay, so it's exactly the same statistic as for a random permutation. Right, so that's one example of the Chebatarov density theorem, right? So here's that same product appearing in Cauchy's formula for permutations. So the moral is that the statistics of factorization type match exactly the statistics of the cycle type of a random permutation. All right, so that's very classical. Also take the point of view of fixing a field, FQ, and then taking a random polynomial over that field of degree m, where m we think of as large or as going to infinity slowly, say. Then the number of irreducible factors with a given degree also behaves like a Poisson random variable with parameter 1 over k. And these are quasi-independent as long as k is small compared with m. Okay, so that's a much more recent theorem of Aratia, Barbour, and Tavare. So the moral is, in either case, we obtain this Poisson distribution with independence for the, let's say, the small or the small and intermediate degrees and the small and intermediate. So here, of course, there's no restriction. Here we have to restrict to the degrees because, for example, let me just give you an example. So let m be fixed. And suppose I want to study the irreducible factors of degree larger than m over 2. Well, these are not independent, right? There can only be one. So these different statistics are very dependent on each other. Yeah. And that dependence is actually already built into the Chebotarev theorem, because we're given that the sum of the the sum of the degrees of all the factors has to equal m. Okay, that's built in as an assumption on R1 through Rm here. All right, so in summary, we have now 3 results: one for primes, one for permutations, one for polynomials, which all look very similar. Okay, but you have to set up the right normalization for primes. So if we look at the statistic that counts primes in an interval of type e to the k plus 1, or we look at a random permutation and look at how many k cycles it has, or how many irreducible factors of degree k a random polynomial has, these are all going to be approximately Poisson with parameter 1 over k. And moreover, we have quasi-independence as long as k is not too large, right? Since our integer here is below x, I want k up to log x. So there's a logarithmic scaling that goes on in the integer setting. Okay, so as long as we have these, this k is not too large in each of these 3, then we have approximate independence for different values of k, right? So k equals 1, 2, 3, 4. These are they're going to be semi-independent statistics. So what it leads to is a common Poisson model for all 3 of these statistical problems. So over the integers, permutations, and polynomials. So I'll let z sub k be Poisson with parameter 1 over k. So this is a genuine random variable now. And these, for different k, these will be independent. Okay, so these are now just purely random quantities, which are truly independent. Then the vector of these random Poisson random variables will model the factorization of an integer into primes, the factorization of permutation into cycles, and the factorization types of polynomials over a finite field. Okay, so this is the common Poisson model, which we are now, it suggests that to study all of these problems, we have reduced it to studying a single problem with purely probabilistic nature. Now, of course, there are many problems for which this model will fail. For example, if we are in the integer setting and we're trying to study smooth numbers, okay, that's a property of the larger primes. The larger primes play a big role in that theory, and this model then breaks down. Okay, so as long as we're studying some problem where the large prime factors play a relatively small role, this Poisson model will be very good for us. It'll tell us approximately the truth. Okay, and what I mean is we want to study the probability that either primes or cycles or irreducible factors have some property, and we study the same problem with these independent variables here, which is usually much easier, although it's not always going to be easy. And that gives us at least a guess about what the truth should be. All right, so in particular, we can count the total number of, how to say, primary factors in each of these problems. That is, we can, let's say, count the total number of prime factors of a random integer, or the total number of cycles, or total number of irreducible factors. And the idea now is that that will be modeled by the sum, z1 plus z2 up to zn. Okay, but the point is that the sum of independent Poisson random variables is itself a Poisson random variable whose parameter is the sum of the parameters of the individual variables. So this will have distribution Poisson with parameter being the harmonic number, which is approximately log n. And then using another idea, which is a special case of the central limit theorem, the Poisson random variable with large parameter approaches the Gaussian or normal distribution, with the mean and variance both being that parameter. So with an appropriate n for each of the problems we're looking at, this is going to be what we would expect to be true. And this has been proved in each of these cases. In the integer case, this is a very famous theorem of Erdős and Katz. So here, n, okay, the n here and the n here are not the same n. So here the little n is a random integer up to x. And then this little n would be something like log x, right? Because we're looking at this logarithmic rescaling. So then if I let e of x be double log of x, then we expect this statistic to have mean and variance ex. And that is exactly the, in fact, this is actually just a special case of the Erdős-Katz theorem. Their theorem covered general additive functions, not just omega of n. So that's what this is saying. On the right side is the cumulative distribution function for the Gaussian normal. And then here we have the Erdős-Katz statistic. Okay. Very similar. Okay, so here's the Erdős-Katz theorem again. I guess this was supposed to be an x here, and this is supposed to be an x. And I think this is supposed to be an x too. Yeah. All right, so some typos here. The analogous result for permutations was proved a few years later by Goncharov. So if C of sigma is the total number of cycles in a random permutation, then this also has mean and variance log n with a, okay, n is now the size of the permutation group. And so that also approaches the Gaussian. Now, Goncharov's proof was actually somewhat different because the statistics C of sigma, there are some exact formulas related to Stirling numbers of the first kind that can be brought into play here. Okay, so it wasn't a purely probabilistic argument, although you can give one along the same lines as we've just seen. And this, I haven't seen I don't know an exact reference for it, but it follows almost immediately from the theorem of Aratia, Barbour, and Tavare. Okay, which says that the total number of irreducible factors of a random polynomial will approach the Gaussian. We also need the degree going to infinity, so you have to be a little bit careful here. But so all three of these problems now have essentially the same answer, provided you scale things properly with the primes, but with an extra logarithm. Okay, so that's just one example of a problem where the large prime factors play a relatively small role. Okay, these are omega of n is, in this problem here, is going to be mostly determined by the smaller prime factors. Okay, for example, prime factor is bigger than x to the 1/3. There can be at most 2 of them, okay, which will be completely insignificant compared with e of x. All right, now on to a little more complicated statistic, and that is to look at divisors and a probabilistic model for divisors. So recall that our model of primary factors, that is primes, cycles, and irreducible factors, came from looking at a vector of independent Poisson random variables with parameters being these harmonic, just reciprocals of integers. So now, given a vector R1, R2 up to RT, I'm going to define this set D of R1 through RT, which will be the following. It'll be the collection of all numbers you get by taking M1 plus 2M2 up to TMT, where MJ is between 0 and RJ. It's an integer here. Now, a little more, how do you say, suggestive way of defining this, which I could have done, is this is the set of all subset sums of a multiset consisting of R1 ones, R2 twos, threes, and so on. Okay, so we're looking, we form divisors from subset sums where this vector represents R1 primes of, say, size 1, whatever size means in the different contexts, R2 prime factors of size 2, R3 factors of size 3, and so on. And then plugging in these Poisson random variables, we then have a random set, which I'll just refer to as script D. And I'm not going to specify what T is here, but you can, for the integer case, if you're looking at integers up to X, you'd take T about log X. For permutations in the symmetric group SM, you take T to be M. And similarly, here you would take T to be the degree of F. But so then, since this D, the set D, counts or represents the subset sums, then in the integer setting, whether a number k is in D or not corresponds to the existence of a divisor of approximately e to the k size. Right? So this is not a perfect correspondence because the prime factors are, if they're in these exponential intervals of length 1, if you multiply many of them, the interval somehow expands a little bit. Okay, but this is the right way of thinking about divisor problems where you want to localize the divisor. For permutations and polynomials, the correspondence is exact. So for a permutation, whether or not k lies in the set D corresponds exactly to the existence of a divisor of size k. Remember, a divisor, tau, is a product of sum of the cycles. And then the correspondence here is also exact. So whether k lies in D corresponds to whether there is some factor of f with degree k, irreducible or not irreducible. Okay, so if you want to study these types of problems, then this studying the behavior of this random set D is, how to say, the right starting point. Okay, if you can understand this problem, you can usually understand the corresponding problems over integers, permutations, and polynomials. Okay, so let's just look at an example to make sure we're all on the same page here. So this is this random, okay, so this is a subset sum where you have R1 ones, R2 twos, and RT t's, etc. And so I'm not doing anything randomly here. I just want to illustrate with a particular vector. So the vector 2, 0, 0, 1. So that corresponds to 2 primary factors of size 1, none of size 2, none of size 3, and 1 of size 4. So that would correspond to a permutation with 2 fixed points and a 4 cycle and nothing else, or to a polynomial with 2 first degree factors and 1 fourth degree factor. Okay, so this is just to understand the notation. So then D of 2, 0, 0, 1 would be the the subset sums of the multiset consisting of 2 1s and a 4. So it would be this set of numbers, okay? And that corresponds to the set of divisor sizes. The set of sizes of divisors of sigma and the set of degrees of the factors of this polynomial. Oh, by the way, this is mod 3, not where everything is over a finite field here, not over the integers or rationals. Okay. So that's just to make sure we're on the right page with notation. So here's a theorem that I proved together with Sean Eberhard and Ben Green a few years ago. If I take this random set here corresponding to these Poisson random variables, and I ask what's the probability that K lies in the set? Okay, this is between 2 positive constant multiples of this quantity here, where this exponent E is a small positive number that appears a lot in these divisor problems. Okay, it's a very common occurrence to see this exponent. Now we stopped at ZK because I could have extended this to an infinite sum, to an infinite list, but ZK plus 1 and ZK plus 2 and so on, they play no role in whether K belongs to the set or not. Because then I would have subset sums with parts that are K plus 1 and larger. So you can never achieve K using those. Right, so that's why I stopped at K here. So the point is this is going to 0 at a very specific rate. And the line on the corresponding divisor function. So how many integers up to x have a divisor in a, let's say, a dyadic interval? So it has this order of magnitude. And so the ideas we used, we adapted the ideas from my papers to this random setting and then applied it later to permutations and polynomials. One interesting corollary is, which is very cute problem due to Erdős, to count how many distinct numbers are in an, let's say, x by x multiplication table. But again, you're counting the distinct products in the table. So it's a bit less than x squared, which is the total number of entries. Oops. And it's exactly this, this exponent making an appearance. In this problem, again, we've bounded it between 2 constant multiples of this quantity on the right. And it's an open problem to find an asymptotic formula, although there is some rough heuristical argument by Pomerantz that says that it might not exist. That is, an asymptotic might not exist. It might, the ratio of left and right sides here might undergo some slow oscillation. All right, but that's completely open at the moment. All right, so here are the analogs now over the in the permutation world and in the polynomial world. So if we take the probability of a random permutation in SM having a divisor of a certain size, then we get this exact same ratio. And moreover, it's uniform in all possible K. If we let M be even and K is N, what this is asking for is the probability that a random permutation has a perfectly balanced factorization. So it factors as a product of two divisors, each that has size exactly half the size of sigma itself. Okay, so again, that's the answer now, with this special exponent being about 0.086. Another corollary of our work is the analogous result over polynomials. So if we count how many polynomials, without loss of generality, let's assume it's monic. Have a degree at most m. I guess it should be degree. Actually, I want it equal to m. That's actually true in either case, but I want the probability that there exists a divisor that is some factor of degree k, whether it's irreducible or not. Okay, so the same factor appears here, and these two results are both corollaries of this theorem here in the random setting by a relatively short deduction. Okay. So again, here are I guess just I'm summarizing the conclusions. So in the integer setting, the multiplication table, which is essentially asking for integers below x squared that have two divisors that are very close to x, so very close to the number's square root. And this is a more exact problem in the polynomial and permutation settings. So we want perfectly balanced factorizations in both cases. So, and we have essentially the same answer in all three. I want to take a little bit of time here and mention some related problems. And so these are what I would call restricted multiplication table problems. We look at, let's say, how many products A times B there are with A and B both below X, but both belonging to some set A. So for an arbitrary set A, M star is the corresponding problem where I only force one of the factors to be a member of A. So B is unrestricted. So this has been studied in a few cases. In the case of, let's say, rough numbers, so that is integers without small prime factors, I found the order of magnitude for the M function. That is, I require both factors to be, say, rough numbers. As far as I know, this has not been done for smooth numbers, so it's an open problem. And again, I would expect there to be some change of behavior as y passes through at least one threshold, whatever that threshold is.
Sorry, Kevin, are you saying the multiplication table for smooth numbers? Is that the problem?
Yes, well, both of these, where you restrict either both factors to be smooth and therefore the product is smooth, or you only require one factor to be smooth.
Yeah, so a student of mine, Mazia Medizada, has
so he did study this problem. Okay.
Yeah.
Probably with the M function, right? Both factors being.
Yeah, both factors. Yeah,
right.
And you're right. There is a difficult y range.
Yeah.
The transition between two behaviors.
Right. Yeah. Okay. Great. well, I'll update my slides after the talk then. If we restrict the prime factors to say an arbitrary set of primes, this is also, I think this is completely open, except, you know, if you remove small prime factors or remove the large ones. But if you remove an arbitrary set, that's a completely open problem. Permutation analogs, as far as I know, I haven't seen any papers on restricting the factor, okay, to some set B. You could restrict B to being, let's say, having certain size restrictions. So either size bigger than some parameter or less than some parameter, and that would be analogous to rough numbers and smooth numbers for the integers. But for other numbers B, this I think this is pretty much open. There's another type of restricted divisor problem that I want to mention. And here I'm restricting the product to be in a certain set. So then so I'm formulating this slightly differently. I want the product to be in a certain set, but I want a divisor in a particular interval. Okay, so in a couple of examples, there's been some work on this for, let's say, a shifted prime. I came up with an upper bound, and then Dimitris Koukoulopoulos supplied the much harder lower bound of the same order of magnitude. If the set A is the set of values of a fixed polynomial, this is a problem that has received a lot of attention because of its connection to something called the Chebyshev problem. So Erdős and Schinzel and Tenenbaum worked on this in the 90s. And then I have a paper with Xian from last year, getting the order of magnitude when y is, let's say, not too large. But when y is of size x, the results are poor. And that is, in fact, the most interesting range of y because of this theorem of Erdős and Schinzel. So what is the Chebyshev problem? It's to understand the maximum prime factor of any value of a polynomial where n ranges up to x, and to prove a lower bound on that that's as good as possible. And so there's relatively easy arguments that will give you something of size x, but doing better requires much more work. So Erdős and Schinzel proved a very general statement that the maximum size of a prime factor here is at least x multiplied by a factor which depends on this restricted divisor problem. And it's exactly with y being x over 2. So g is the degree of the for this problem. And so we need y of size x. Now, the best result, that is the best lower bound on this restricted divisor problem, is due to Tenenbaum. It's x divided by a power of log x, which is log 4 minus 1. That's about 0.386. A naive heuristic would suggest that it should be of size x over log x to this special exponent, which is much smaller. And that would immediately produce improvements in all of these Chebyshev type problems. Right. So as far as I know, this result of Tenenbaum has not been improved in general for general F. Okay, there's a lot of work been done on very special low degree polynomials in particular, but not for general polynomial F. Okay, and in the last few minutes of the talk, I'll mention this joint work I have with Dimitris and Ben Green. That so this is the subject of Dimitris's talk back in October, we're looking at this concentration function called delta, the delta function. And so I look at any dyadic interval or semi-dyadic interval, and I want to count the maximum number of divisors that appear in any such interval. And a lot of the motivation for studying this came from an old conjecture of Erdős that stated that the delta function is at least 2 for almost all n. Of course, there are lots of numbers you can come up with for which this is not going to be 2, primes, for example. But if you take typical numbers n, that was the conjecture. It was proved in 1984 by Maier and Tenenbaum. And moreover, they showed in a later paper that for most n, the delta log function. They also, these two authors conjectured that the lower bound was close to the truth because it came from a certain heuristical argument. The log 2 was some artifact of their method. They didn't think it was telling the truth. So this function has since, in recent decades, been applied to many problems in number theory, in particular in additive number theory. So although this is a purely multiplicative problem, it's had applications to various problems using the circle method, so on. So now, the main idea that I had, or one of the main ideas in this paper with Green and Koukoulopoulos, is to use this Poisson model that I talked about on earlier slides. And moreover, we're going to simplify the model with another level of simplification, using the fact that a Poisson random variable with a very tiny parameter is essentially a Bernoulli random variable with the same parameter. In other words, a Bernoulli random variable takes only the values 0 and 1. So the probability that the Poisson variable takes a value 2 or larger is something like 1 over n squared. And since the sum of those converges, then that implies that this is going to be a very good approximation. So now a Bernoulli random variable, if we have a vector of those, that's a 0, 1 vector. And the positions where we have 1, we can call that a set. So we'll call that a random harmonic set, where each number is chosen to be in the set with probability 1 over n. And then what we care about, which I've now motivated, is what I'll call FA, which is looking at all the subset sums, which are these guys here. But instead of just looking at the set of subset sums, we're looking at how many times a particular sum occurs as a subset sum and taking the maximum of the number of occurrences. Okay, so this is now a concentration function. Let me give an example, if that was a little too fast. So we take the set 1, 2, 4, 5, 7. Let's say those are chosen to be in our set. Then f of a will be 3 because there is a particular number. Actually, there are two numbers, 7 and 12, each of which have 3 representations as a subset sum from A, right? 7 is either 7, 5 plus 2, or 4, 2, 1. Okay, so this would have a concentration value of 3. So then our main problem is to take this random subset, let's say up to n, and study the statistics of this concentration function. And what we proved in this paper, which was a very long technical proof, but we proved that within the set 1 through n, we have a concentration at least log n to a particular power, and that power is about 0.353. And as a sort of easy corollaries, we achieved a lower bound on the delta function for almost all n and corresponding analogs for permutations and polynomials, which followed by just a few lines once we had this main theorem here in gray. Okay, and now I point out that this number 3.353 is slightly larger than the lower bound given by Maier and Tenenbaum, which indicated that their conjecture was wrong. We have conjectured that our exponent is actually the correct one here, that there should be an equal sign here rather than just a lower bound, but we don't yet have an argument to supply that. And then the last thing I want to talk about is a restricted problem where we restrict our set to be, let's say, between 2 powers of n. And we call this quantity beta sub k, which is the largest value of C for which this set will have concentration value at least k with high probability. So you can see as the number C increases, it becomes less likely for this set to have a given concentration value because it's a smaller set. But when I make C smaller, then this is a bigger set, and it's then more likely. So then what is the largest there? Well, again, a corollary of our work is that we have then a lower bound on beta k. Okay, this actually is giving us a lower bound, which is related to this special number here. Now, the number beta k is connected with a problem of how close can 2 divisors be of a typical integer. So here we're looking at intervals which are smaller than dyadic because this quantity alpha is bigger than 1. And so almost all integers will have a divisor in such an interval, that is for some y, for any alpha smaller than this ratio here. And in future work, it's not really in the paper we have on the archive, but in future work, we've determined the exact values of beta 3 or better than corresponding values of Maier and Tenenbaum. And for this problem, we've then improved on Tenenbaum for every k greater than or equal to 3, right? So the value of beta 2 has been known for quite some time, exactly what it is. These two, in fact, have exact expressions, but I don't expect the larger ones to have exact sort of nice expressions like involving logarithms and so on. Okay, so yeah, I got a little technical at the end, but that's where I will stop.
So, okay. Thank you for the. We have time for questions. So, if one of you guys have a question, please. Okay, for maybe I have a silly question. Can you return to your screen, please? Your PDF. Return just one.
My PDF. I'm still sharing it. You're not seeing it?
Yeah. Please return to the previous page. Yeah, you see that you talked that for almost n, you believe that the delta n should be equals to log n to zeta minus 2 to zeta minus little o of 1.
Right. There, we conjecture that there's an upper bound with, say, zeta plus little o of 1. Yeah.
Okay, but uh, I, I'm not so sure because you said that you believe that this is should be an equality, right?
Right. Yeah.
Right. I do not understand what
You don't
why
understand what I meant by that?
yeah, what do you mean because this should be an equality?
Yeah, well, what I mean is the conjecture is that for almost all n,
Mhm.
delta n equals log n to the zeta plus little o1. Okay, there's some function over here which is indicated by this little o1. So in other words, it's bounded between two powers of log that have essentially the same exponent, you know, zeta plus epsilon and zeta minus epsilon.
Oh, I see.
Well,
Okay.
remember, there's a gap here. There's a substantial gap between these two exponents.
Oh, yeah, I see.
Log 2 is about 0.69, and this is 0.33. So,
Okay, and zeta is equal
right.
dot 35. Okay. And just another thing. When you talk about finite field, if you take Q equals to 2, maybe it's terrible. It's the worst choice.
Yes, generally, we would want the field also to be large in some sense.
In some sense, okay.
Yeah. I think I maybe briefly went over that in some earlier slide, but yeah, otherwise the statistics of just counting, say, irreducible polynomials of a certain degree, you have a main term which depends on Q, and then a secondary term which is a smaller degree, and you really want Q to be large for that to
I see.
have a
Okay. Thank you. So guys,
so I have a question, sorry. So how to, still on this page, how to get the corollary from your theorem for the lower bound for FA, and then you get the lower bound for
I didn't quite understand the question. Are you referring to the polynomials?
I mean, so the theorem you have for
so how do you get from this theorem to these
to the corollary? Yes.
Oh, well, you just show that this random set A is a very good model for the prime factors of a number, let's say, that are not too small, because in fact, we really don't care about the really small prime factors. So you show that that's a very good model, and then it follows in just a few lines, right? So you have a concentration of this quantity that implies a concentration for actual integers. And then the same thing for, but you have to make this very qualitative. I mean, you have to be very precise about what you mean by good approximation. So it has to be uniform over all the uniformly in a pretty big range within, let's say, 1 to x. Yeah. But that's basically the consequence of something called the Kubelius model of integers, which is a quantitative statement saying essentially the same thing. Yeah.
So more questions? So if not, thank you, Ford. Thank you again.
Right. Yeah, thank you again for inviting me.
Oh, it's a pleasure. Thank you.
For taking the time.
Okay, so I will stop the record.
Right? Mhm.